Good morning, dear students. My name is Ferhan Mazher, and today we are studying the subject Cambridge O Levels Physics 5054. Today we have set our hearts to solve alternative to practical paper. We call it ATP paper. We also call it paper 4. And today we have selected May-June 2022 4-2 paper. So this paper 4 belongs from the zone 2, and the time allowed for this paper is 1 hour. So let's start today's paper. So May-June 2022 4-2 paper. We call it paper 4, alternative to practical, or we call it ATP. 1 hour time is allowed. And here we go to the first question. The question is, a student determines the thickness of the glass in a test tube. The student uses a ruler and two rectangular wooden blocks to help him measure the external diameter, capital D, of the test tube. Describe with the aid of a diagram how the student determines an accurate value for D. It's a 1-mark question. So the space is given to draw the diagram and write the description. So here we have that diagram. So you can see I have tried to show this is that test tube, and these are two wooden blocks. The test tube is between the wooden blocks, and I have put a scale, a ruler here. So I will check what is the distance between the two wooden blocks. Whatever will be the distance between the two wooden blocks, that will be the external diameter, or you can say capital D. So let me read it. The answer I wrote, put test tube on table between two wooden blocks as shown in the diagram, or as shown in the figure. Measure the distance between the two blocks with the help of a scale. This distance is equals to the external diameter of the test tube. It's a 1-mark question. Hopefully you understand how this will be done. And this is its diagram. So let me take out the marking scheme also, so we can also have a look at the marking scheme. So okay. So this is A part. I think you can see the marking scheme. Okay, so we are going to the next question. He says the student clamps the test tube in a stand, fills a measuring cylinder to the 100-centimeter cube mark with water, pours some water from the measuring cylinder into the test tube. The arrangement of the apparatus is shown in the figure 1.1, and the test tube containing water is also shown full size in the figure 1.1. So here you have the stand, and this is that test tube in the clamp, and you have added some water in it. And this is a zoomed view of the test tube. This is the height of the water in the test tube, and this is the external diameter of the test tube. So this is that full scale, not to the scale, full size diagram. Measure the height h of the water in the full size test tube in figure 1.1. So underline this word measure. When they say measure, it means that you have to use your instruments to actually measure it. So they ask us to measure this full size diagram. Here you have to measure h. They want us to measure h. So I will try to measure it with the help of the scale. Record the h in the centimeter to the nearest millimeter in the second row in the table 1.1. The table 1.1 is here. Here. In the second row, we have to fill that. The H value, whatever you will measure, whatever will be the answer, you will add here. I have measured it, and that value was 3.2 centimeters. I measured it and it was approximately 3.2 centimeter. According to the marking scheme, it's also right. Then they say figure 1.2 shows the volume VR of the water remaining in the measuring cylinder. So in this measuring cylinder, the water was 100 centimeter cube. After you poured some water from the measuring cylinder into the test tube, now the water in the measuring cylinder left is this much. It is 89 cubic centimeter. Shows the volume VR of the water remaining in the measuring cylinder. Record the VR in the table 1.1. Calculate the volume of the water in the test tube. So this VR will be 89 centimeter cube. The volume of the water which you have put in the test tube, that will be 100 minus 89. So let me show you. So the VR value is 89. So the V value which you have put into the test tube, that will be 100 minus 89. So that will be 11. So that's why I've written 11 here. Let me check the marking scheme, 89 and 11. Okay, so we are doing good. Okay. So we are done with that. The student adds more water from the measuring cylinder into the test tube, measures and records the new values of H and VR in the table 1.1. Repeat the procedure for 3 more values of H and VR. The results are shown in the table. So, and that table I can show you from here. We have filled it. So these are the different values of H. These are the values of the VR. This is the volume, which is in the test tube. So they say on the grid provided, plot a graph of the V. This is V. On the y-axis, the V will be on the y-axis, and against H on the x-axis. This H values, they will be on the x-axis. Okay, so they will be here, and the V values will be here. If you look at carefully, and he says start both axes from the origin 0, 0. Draw the best fit straight line. Okay, these values here, they are going up to 14. The values of H, they are on the x-axis. The values of the V, they are going to 53, approximately 60. So let me show you. Okay, so first of all, I will, on the x-axis, the H is shown, that's in centimeters. So I will write here 2, 4, 6, 8, 10, 12, 14. So I will label this thing also. And on the y-axis, we will represent the V. That will be 10, 20, 30, 40, and 50. That's volume in centimeter cube. Then I will plot these points. At 3.2, the HV is 11. At 3.2, 11. Okay. Then you have 5.6. At 5.6, you have 21. So I will plot that at 5.6. This is 5.6. This is 5.6. That will be 21. Okay. And then you have at 8.9, you will have 34. At 8.9, 34. And then you have at 12.5, you will have 46. At 12.5, at how much? At 12.5, you have 46. And at 12.5 is this point, 46. And at 14.2, you have 53. 14.3, you will have, how much was that? 53. Okay, so I'll put that dot. So once you have put the dots, then you will draw the line of the best fit. We will try to draw the line of best fit in such a way that it is in that same pattern in which the dots are. And the number of dots above the line and number of dots below the line, you try that they are equal to each other. So I have tried and I have drawn this line. So that's the line of best fit. Now the question is, once you have drawn the line of the best fit, then they say, calculate the gradient M of your line, show all working and indicate on the graph the values you use. Okay. So if you want to find out the gradient of this line, the method is very simple. You take 2 points on this line of best fits. For example, I've taken this point, that's 4,15. I've taken this point, that's 12,44. And I will apply the formula of the gradient, that is rise by run. So I joined these points and I completed a triangle. This is rise and this is run. So the gradient is rise by run. So I will show you how I found the gradient. So you can see here, this is that graph. Okay. So I have taken 2 points, 4,15 and 12,44. The gradient in your mathematics, you remember, the gradient formula is y2 minus y1 divided by x2 minus x1. It will be 44 minus 15, and in the denominator, you will have 12 minus 4. And when you do this calculation, it will be 3.625. So you can say it's 3.6. So that we know, now we know the gradient. Now the next question is, she say if the test tube is a perfect cylinder, then the internal diameter D is given by the equation D is equal to square root of the 4m by pi. Use your values of the m in the E first part and the equation to calculate the internal diameter. Okay, just very simple. The formula is given. The value of the m we just calculated is 3.6. So just put that value. So you have 4 multiplied 3.6 divided by pi equals to square root answer equals to. You will get 2.17. Just put the values and do the calculation. So the internal diameter is 2.17. Your values for the D is approximate. State one difficulty in measuring the height h of the water in the test tube and suggest how this difficulty can be overcome. So there are so many difficulties because the water is in the test tube. So when you will use a scale, the scale will be outside the test tube. So there will be some distance between water and the scale. Another thing is that when you try to bring the scale near the test tube and when the scale will touch the test tube, the, the test tube will shake and the level of the water will be not steady. Another thing is that you can hold the test tube in your own hand and you can put a scale with it, but even then your hands will have a little vibration, shake in them. So that's a big problem. So the one difficulty which I wrote is level of the water is not steady due to shaking of hands if you are holding the test tube in your hand. So how you can overcome this suggestion is put the test tube on the table and hold a set square with it to keep it vertical. And when you hold the test tube in your hand, it's not possible to make it perfectly vertical. So the one thing you can do is you can put the test tube on the table and then you can use a set square with it to make sure that the test tube is vertical. If the test tube is little inclined, the level of the water will change. You have to, by use of the set square, you have to make sure that the test tube is perfectly vertical. And the scale which you put with the test tube, that should also be vertical. So you can use set squares to check if they are vertical or not. Then in this case, suggest, then the question is, then the question suggests another reason for your, why your calculated value for D is only an approximate. You see, the D value is coming from the M value gradient of the graph, and that gradient came from the V value and the H value. The V value, the volume of the water in the test tube, that was only accurate up to 1 centimeter cube, and the H, you measure the height of the water in the test tube. That is an approximation, because the bottom of the test tube is not flat. The bottom of the test tube is It's spherical, so it's not flat. So H is a little approximation. So that's why the D value is an approximation, because all the inputs which you have put into in calculating the small d, there you have made a little bit approximations. So V is accurate up to 1 centimeter cube, and H is approximation because bottom of the test tube is round, it's not flat. So let me show you the marking scheme. So these are the answers. He says measure the external diameter capital D of the full size test tube in the figure 1.1. So the diagram which was on the first page, 1.1 figure here. So measure with the help of the scale this external diameter. Put a scale here and measure how much is this. And so when you actually measured it, it is with the from the paper, it was 2.4 centimeter. Okay. So this is the answer. So then they say use your answer for the E second part and G first part to calculate the thickness of the glass. The thickness of the glass will be, external diameter minus the internal diameter, and then you will divide it with the 2. So 2.4 minus 2.17 divided by 2, and that will be 0.115. So it will be 0.12 centimeter. We rounded it off. So it will be 0.12 centimeter. Okay. Our answer is right. So we are done with this question. Now we are going to the next question. He says, a student investigates the cooling of hot water in a beaker. The student measures the room temperature before starting the investigation. The room temperature is 24.0 degrees centigrade. The student pours 150 centimeter cube of hot water into a beaker, places a thermometer in the hot water, waits for 30 seconds, reads the initial temperature of the hot water and starts a stopwatch, records the temperature theta of the hot water every 60 seconds for 300 seconds. The students' readings are shown in the table 2.1. So when the time was 0, when you started your stopwatch, the temperature was 89.5. When the time was 60, the temperature was 83. When the time was 120, the temperature was 77.5. At 180 seconds, the temperature was 73.0. At 240, the temperature is 69. At 300 seconds, the temperature is 66.0. He says, suggest why the student waits for 30 seconds before reading the initial temperature of the hot water. You see, whenever you put thermometer in the hot water, you give it some time so that the temperature of the whole water body is uniform. Plus, you also give a thermometer some time so that it can respond to that temperature. So that there should be enough time that the thermometer can show that temperature, because in the liquid in the thermometer, that will absorb the heat and it will expand. So, and it will go to its highest value, whatever possible at that temperature. So you have to give time to thermometer so that it can respond to that temperature. It can show that reading. Okay. Allow thermometer to respond to the temperature of the hot water. That's why you waited for 30 seconds. Calculate the average rate of cooling R1 of the hot water during the first 60 seconds. Use the equation. So that's the equation. R1 is equal to theta 0 by minus theta 60. and the whole thing divided by 60, where theta 0 is the temperature of the hot water at the start, and theta 60 is the temperature of the hot water after 60 seconds. So we can see at when the time was 0, initial temperature of the hot water is 89.5, and at 60 the temperature is 83.0. Okay, so I can put those values in this formula and very easily calculate the rate. So the rate will be 89.5 minus 83, and the whole thing divided by 60, and that will be 0.108. So that's the rate. It means degree centigrade per second. So with this rate, the thing is cooling down. Calculate the average rate of cooling R2 of the hot water between 240 seconds and T 300 seconds. So at 240 seconds, the temperature is 69. At 300 seconds, the temperature is 66. So this happened in 60 seconds. So the rate will be 69.0 minus 66, and you divide that whole thing with the 60, so you get 0.05. So this is the rate of the cooling. Before, the rate of the cooling was 0.108 degrees Celsius per second, and now it is 0.05. So the rate of cooling has dropped. Use the values for you calculated in the part B to describe how the rate of cooling of the hot water changes as the hot water cools. So rate of cooling has dropped from 0.108 degrees centigrade per second to 0.05 degrees centigrade per second. So their question is, and well, so this is question number 2. It's marking scheme showing up on your screen. He says at the end of the investigation, the student leaves the water in the beaker, predict the final temperature of the water after 2 hours. So you see the final temperature of the water will, when you let it be on the table for 2 hours, so the water will lose its heat, and its temperature will become equal to the room temperature. And that room temperature is 24 degrees centigrade. So the final temperature of the water after the cooling will be 24 degrees centigrade. He says, suggest how the student ensures that temperature readings are as accurate as possible. You see, you are measuring the temperature and the time. So you can use a digital thermometer. When you use a digital thermometer, it becomes very easy to use, very easy to read. On the liquid in glass thermometer, it takes some time to actually measure, actually read what is the reading. But on digital thermometer, there will be a digital display, so the temperature will be very easy to record. So I think it's over. Question is over. So the whole question number 2 is showing up on your screen, and you can pause the video. You can take your time with this question. Okay. So then the question is, I just calculated R2. Do we have further questions on this? Okay, so we are done with this question. The last part is suggest how the student ensures that how the student ensures that the temperature readings are as accurate as possible. So you can use a digital thermometer. We are done with this question. Okay, so we are going to next question. The next question is question number 3. 3 students A, B, and C measure the speed of sound in air. Student A and B stand at opposite ends of a football pitch. Student A strikes 2 large blocks of wood together. Student B starts a stopwatch when she sees the blocks hit each other and stops the stopwatch when she hears the sound. The student repeats this procedure twice. Student C measures the distance D between student A and B. Okay, the time T recorded are shown 0.45 seconds, 0.41 second, 0.51 second. Calculate the average value of the T. Give your answer to two significant figures. So if you want to find out the average value of the T, you just add these three values and whatever will be their sum, you divide it with the three. So you can see here, so 0.45 plus 0.41 plus 0.51 equals to, and you divide the sum with the 3, and that will give you 0.456, which will mean 0.46. So the average time is 0.46 seconds. Then the question is the distance, the small d between the student A and B is 119 meter. Suggest a device that can be used for measuring this distance. 119 meter, you can use many instruments, but one of the good and easy instrument is trundle wheel. It's basically a wheel which has a handle. You can hold the wheel from the handle, and as you walk, the wheel do the revolutions on the ground, and each revolution corresponds with a certain distance. So it can tell you by counting how much revolutions the wheel has made. So it has a small automatic digital system which counts how many revolutions the wheel has taken while you are walking. And then by from that circumference of the number of revolutions is multiplied with the circumference. So that tells you how much distance is traveled. Okay. So we can use the trundle wheel, then their part is calculate. Okay. He says calculate the value of the V, the speed of the sound in the air, use the equation. Okay. So, so V is equals to D divided by T. The distance traveled is 119, and the time taken to reach from one point to another point, which are 119 meter away, is 0.46. So that will be 25.8. So 25.8. So I said 25.8 is 258.6. 258.6. Sorry, I said the 25.8. It's 258.6. So that is the how you calculate the speed, velocity. So that's the marking scheme showing up on your screen. Then the question is suggest one reason why the value calculated in the B second part, for the speed of sound in air is only an approximation. So you see the time which you have shown here, 0.45 seconds, 0.41 seconds, 0.51 second, that time is very short. So the is almost equals to the human reaction time. So when you are trying to measure so small time interval, the human reaction time will affect that value because that time which you are measuring is very short. So in the human reaction time, you start, you stop, you start the stopwatch, you stop the stopwatch. So the human reaction time will be a large portion of this value. So it will be affected by that. That's why we are saying it's approximate. Time measured is very short. It is affected by the human reaction time. It's very short interval. You see, this is the marking scheme. And this is question number 3. Okay. He says the student investigates how the resistance of a filament lamp changes with the current through it. Through it is varied. The student connects the circuit shown in the figure 4.1. The student has connected the circuit incorrectly. In the space below, redraw the circuit with the voltmeter and ammeter connected in correct position. You are talking about the lamp. So this ammeter should not be here parallel to the battery. It should be here in series with the lamp. This voltmeter should not be here on the thermistor. It's variable resistor, sorry. It should be here on the lamp so it can measure what is the voltage drop on the lamp. So their question is in the space below, redraw the circuit with the voltmeter and ammeter connected in correct positions. Okay. So here we have that battery, here we have the ammeter, then we have the lamp, then we have the variable resistor, and there's a voltmeter connected parallel to the lamp. When the switch is closed in the corrected circuit, the student observes that the lamp does not appear to light up. The filament of the lamp is not broken and the battery is not run down. What observations does the student make to confirm quickly that the filament of the lamp is not broken? You see, when you will connect this, the lamps have not lit. The lamp has not started giving us light. And the reason can be that the current is very low. So how do I know that the lamp is not broken, but the current is low? Because the ammeter will be showing some reading, but the lamp will not lit. So because the ammeter will be showing some reading, that means that the filament lamp is not broken. Then the question is, suggest why the lamp does not appear to light. There can be many reasons, but the current is too low because the resistor circuit is very high. So the current coming from the battery is low. So I think, my dear students, the paper is over. That was so, my dear students, today we have done May June 2020 2002 to Physics 505442 ATP paper, alternative to practical. In this single video, we have completed the paper. I have tried my best to explain you the concepts and the ideas involved. So I hope you will like this video. If you think that you have learned something from this video, please do share the link of this video onto your Facebook account and onto your Twitter account and onto your Instagram accounts because that will help me promote my channel. I think it's a great blessing for me that I have an opportunity to make these videos and so many people around the globe who are doing their cameras and they can watch these videos and they can benefit by just sitting at their home. They can have A-class past paper practice. So thank you very much, everyone. It's a blessing for you and also for me. Thank you very much. Have a good day. God bless you all.